man. You could make it. You know what? Since you went through all that trouble to make it all the way over here, why don't I teach you about the models of the solar system? Okay, I'll do it. Stop begging. All right. Today we're going to break it down. Remember last year in grade 8? Oh, such a beautiful time. We talked about laws and theories. And we are going to specifically talk about scientific theories today. So just to kind of recap, science as a whole is based on observations. We see something happen, and as scientists, what we want to do is we want to figure out a way how to explain why that happens. Like, oh, the sun appears to move across the sky. Why is that? I don't know. Let's try and come up with a reason to explain it. And so that's what they do. They come up with these scientific theories to figure out a way to explain an observation, something that they've seen happen. And the way that they test these theories and say, yeah, that makes sense, or no, that's totally insane, is they use that theory to predict events that would happen. So they use that theory and they say, okay, if I can predict with this theory that this will happen at a certain time, or this will be located at a certain place, or if I do this 8 more times, then this will happen. And if that prediction is accurate, then they go, oh yeah, that's a nice theory, let's use it. And eventually, if they get to a point where they say, this theory wasn't able to predict that, then they question that theory and say, well, is that theory really true then? Is that explanation that we came up with to explain our observations really accurate? Because it's not able to do a great job anymore. And that's when they either modify that theory or completely scrap it and try to come up with something new that will do a better job at predicting these events. So, scientific theories. What we're going to be talking about is the theories that people have made based on the motion of objects in the sky. So based on observing these celestial bodies. And they've been observing the sky for thousands of years. And of course, over time, scientists have used or figured out theories to help explain why these objects in the sky move the way that they do. And we're going to be going through some of those common theories or those really important theories that have been, I don't know, kind of evolving from the past to what we're at now. Some theories that we're looking at are completely ridiculous with the technology and the knowledge that we have today. But we can keep in mind and we could value the ideas that people once had, even though that they're wrong, because they didn't have that information. And without them, well, maybe we wouldn't see what we do today. So that's what we're going to do. Yeah, I've already said this. So, next slide. Alright. As we have seen some theories, as we get better technology is really the giant shift that causes us to scrap one theory to the next. Because if we have more technology, we could get better measurements, we could get more accurate data, and that accuracy that we can get with technology really helps us question and say, hey, is what we had before really true, or is it time for something else? And really, all of the shifts between old theories and newer theories has been around the development of technology, which is kind of cool because technology is absolutely wild. To think, you're learning right now, you're hearing my voice because of technology. And it's because of these advances in technology that really just change whole ideas and whole models on everything that we thought we knew. All right, let's take a look. The first theory that existed, well, maybe not the first, but the most common theory that existed about Earth way back in the day was that the Earth was flat. They thought the Earth essentially looked like this pizza shape here. It was just this circle. And then the sky was like a dome above it. And that made sense because if you look up into the sky, it looks like there's parts where the sky meets the Earth. and then there's this high piece right directly above us, and then on the other side, the sky meets the earth again. So it kind of looks like this pizza flat shape with a dome or a big bubble on top of it. And from Earth's perspective, to be fair, the earth does look flat, okay? Especially in Winnipeg. So we're looking around us. It doesn't look like the earth is curved. If we put a ball on the ground, it's not automatically rolling around. It'll stay flat. It's not going to roll to one side or the other. And in their defense, from our perspective, standing where we are or sitting where we are, the earth does look flat. And it really does look like there's a dome over the sky, over the earth that makes the sky. However, flat earth, as we know it today, is not accurate. Okay? So Greek astronomers, they were the ones who made new observations that couldn't be predicted by the flat earth theory. So they were the ones who looked at evidence that could not, or that could disprove flat earth theory. And the evidence wasn't ridiculous. It was something that they can find way back in the day. But the first thing of the two major pieces of evidence was that when we had an eclipse, okay, so what an eclipse is, you have the moon, we have the sun, and we have the earth. Well, an eclipse happens when the earth is directly in line with the sun and the moon. We have different eclipses. Sometimes the earth's in the middle, sometimes the moon's in the middle. Different things, different times. But what the Greeks observed is when we had an eclipse like this, where the earth was in the middle, the sunlight that shone on the moon was an eclipse. So it was like a curved shape. So you could see the edges of this shadowy figure to pass across the moon, and it wasn't just this flat, straight line shadow. It was this circular ellipse. It was this curved shape that passed over the moon. And so the Greeks were saying, well, hey, if we are flat earth, that shouldn't be the case. We should essentially see a line across the moon. But instead they saw this curve, so that made them believe that maybe the earth wasn't flat, but rather it's a spherical shape. The other thing that they noticed was that if they were standing on earth, this is flat earth here, make it even more flat, and they had some water, I'm water, and they were standing on the shore, I am standing on the shore, and there's a boat, and it's sailing off into the distance. First of all, they were afraid that eventually if the boat traveled too far, it would just fall off the face of the earth. Terrifying thought. They were always too scared to sail too far because at one point, just fall right off. Which seems ridiculous now, but back in the day, that was a legitimate fear. What the Greeks noticed is when they were watching the boats travel away, the boats would appear to get lower and lower until it disappeared below the surface. Right? Because eventually as the boat travels, of course this curve is a little exaggerated, but the boat is continuing on across the water, but from our perspective, we could see less and less of it until it finally disappears below the horizon. And so these people on the shore would be like, oh my gosh, these people in the boat, they've fallen off the edge of the earth, they're gone, they're dead, they're never coming back. But then all of a sudden, the boat would travel back and be like, hey, what's up, peeps? We've missed you. Oh my gosh. And they'd be like, how are you alive? You've fallen off the edge of the earth. And like, no, we didn't. We just sailed off to the distance and now we're back. And so the fact that they could no longer see them implied that the earth's surface must be rounded, because that would explain why they appeared to disappear but didn't actually. So kind of cool. That's the evidence that the Greek provided. And then the flat earth scientists were like, I have no idea how to explain that. I can't explain why the shadow on the moon is curved. I can't explain why boats seem to disappear over the horizon. None of that makes sense based on my flat Earth model. So they had to scrap that and come up with a new model, which is what our current model is, and that the Earth is spherical. Kind of cool. All right. There's also this guy named Eratosthenes, and what he did was, he was a big math guy. Ugh, what a hunk, right? Look at this guy. Oh, dang, hello. And what he did back in the day is he calculated angles of shadows. And so the sun would shine on something, as a particular building perhaps, and he would measure the angles of those shadows. And crazy enough is that he used those measurements of those shadows to determine the circumference of the Earth, which is absolutely insane because this happened 250 BC. So like 2,270 years ago at this point. That's how long ago he was making calculations of the circumference of the Earth. And so he's doing these calculations, and the most incredible fact of it all is that his calculations were fairly close to accurate. Like, not incredibly accurate, but like pretty impressive for 270 years ago. That's just absolutely mind-boggling to me. Because they didn't have the technology to do that. He just used shadows to figure that out. And so what he did was, he looked at shadows based on some pole in Alexandria. Yeah, this is the pole. And a well. And he knew the distance between these two places. And based on their shadows, he could figure out, well, you know what? I know a circle has 350 degrees, or 360 degrees in it. And if this shadow at the pole at Alexandria is approximately this degree, then I know the distance between these two is 1/50th of what it is all around the world based on degrees. And it's absolutely insane how he did this. And the fact that he was so close to the actual circumference of the Earth is just absolutely mind-boggling to me. It impresses me so much how mathematicians back in the day with limited technology did their things. Such a high appreciation for them. Holy smokes, math is the best. I know, it's the best. Okay. Whew. Anyways, let's get back into other models that exist. And so we're not necessarily going to be talking about models of necessarily Earth anymore. We're going to be talking about models of our solar system. So back in the day, in early civilization, so the 2nd century, we knew other planets existed. We knew that we had a sun, and we knew that we were Earth. Okay? But when we look up in the night sky, we see the sun move across it. We see the planets move across it. We see the stars move across it. Which leads us to believe that we are the center of our solar system. There is us, the Earth. Hi, I'm the Earth. And everything else is circling around us. Because that's what it looks like when you look up in the sky. Right, if you ever are outside and you look at the sun, I mean, don't look at it directly, because that would hurt, but you'll notice that the sun rises in the east, goes across the sky, and sets in the west. So it would be reasonable to believe that we as Earth are stationary, because we don't feel our motion, but our sun is moving around us. And during the nighttime, or sometimes during the day too, we could see different planets. They kind of appear as large as stars, sometimes larger, but we could see these planets, and they also appear to be moving across our sky. So it, again, leads us to believe that we as Earth are stationary, and all of our planets and stars are moving around us. So they called this model the geocentric model. Geo is the prefix for Earth, and centric means centered. So this is the Earth-centered model. And the Earth-centered model believed that just everything, the sun, the moon, the planets, the earth, or the stars, everything revolved around us, the earth. The Greek astronomer, Ptolemy, he was the scientist that was credited for this. So he was the one who said, you know what, this is the geocentric model. This is why I believe that this is the model that's structured this way. This is the evidence that I have. These are the predictions that it can make. And he created a pretty accurate model mathematically. So he mapped out all of the stats, all of the measurements, and it was pretty good. And he was actually able to predict the movement of stars and planets given the measuring abilities at the time. So like we said at the beginning of this lesson, is that the way that we tell if theories are accurate is if they're able to predict things that would happen. And so Ptolemy, he was able to predict where stars and planets would be located at certain points of time. And so that is why people believed the geocentric model for so long. They said Earth is in the middle. Ptolemy could do the math. He could tell you where that star is going to be in a couple days. He's going to tell you where that planet's going to be in a week from now. And those measurements that were made back in the day seem pretty accurate. But again, like what we said, technology was really the key player here in determining or kind of changing our minds about the different theories. Because as soon as we got better technology, and that was around the 1500s, we were able to make those measurements a little bit more accurately. And as we were making these measurements, we could see that Ptolemy's theory wasn't actually able to predict the location of these celestial bodies, so the planets, the stars, etc., as accurately as we thought he could originally, right? So people started to question the geocentric model. They said, I don't know, your predictions are decent, but they're not great. What the heck? What can we do to make our predictions better? And that is when we came up with the heliocentric model. And I say we came up with it, but really Nicholas Copernicus was the guy who proposed the model. But I say we because I feel like we're pretty close, we're homies. And he can't tell you otherwise because he's long gone. But it's true. So, the heliocentric model, he suggested that instead of the Earth being in the center, we're not the center, the sun is the center. And, well, if the sun is the center, that means the Earth is traveling around the sun, and everything else travels around the sun too. And it does so in circles. So here's a picture. Look at him just drawing circles. Whee, circles around the sun. And one of those circles is the path the Earth takes. And one of those circles is the path that other planets take. And one of those circles is just paths that other celestial bodies take, like the moons and things like that. But this model, the heliocentric, so centric still means center. Helio is a prefix that relates to the sun. So heliocentric means sun-centered. This model did a really good job of predicting the positions of the stars. And the heliocentric model is still one that we use today, although there has been a couple of tweaks made. Okay, so right now, this is what Copernicus would have seen. He would have seen the sun smack dab in the middle. Then we have Mercury, then we have Venus, then we have Earth and its moon. Then Mars and Jupiter and Saturn and all that. They're all traveling or revolving around the sun in these circular paths. A couple of tweaks have been made since then. We have Johannes Kepler, and what he said, well, those paths are not exact perfect circles. They're more elliptical. So a circle is almost like this perfect thing, whereas an ellipse is a little bit more of an oval shaped, just for a little bit of context there. Of course, it's not as crazy oval as I've drawn it, but it's not a perfect circle is what the point is. And that was Johannes Kepler, and that's what he kind of made a minor tweak. And then Isaac Newton, he explained why we have those planets in those ellipses or in those elliptical paths around the sun. And he said, well, that happens because the sun has gravity, and the gravity is holding those planets in place and is preventing them from flying off somewhere else into the solar system. So Isaac Newton didn't tweak the theory, but he added to it. So he said, you know what, Copernicus, you're right. With Kepler's little tweak, this all seems accurate, it's making great predictions. I want to help explain why it's doing that. And those planets are staying in this elliptical path or these elliptical orbits because of gravity, which is kind of wicked awesome cool. So, as we continue as a society to grow and create better technology, it is possible that our theories might be tweaked a little bit more and a little bit more, right? The likelihood of our theory to be completely thrown out with where we are with technology today is probably a little bit slim, because going from no technology to a whack ton of technology, you could see a vast difference in terms of the theories from flat Earth to the geocentric model to the heliocentric model. But now that we have quite an impressive amount of technology, as time goes on and technology gets better, we might see some modifications to our theories, but the likelihood of it completely changing and being thrown out and something new coming out is kind of unlikely. The fact that we can use our heliocentric model to predict the location of planets is absolutely insane. But not only can we make those predictions, but those predictions are so incredibly accurate that we've been able to send spacecrafts to different planets, right? Because if you think about it, when we send things to Mars, like our Mars rover, for example, we're not sending a pilot to fly a rocket ship. What we are doing is we have this automated spaceship that will do the traveling for us. We don't have to send people there. And the fact that we have to make all those mathematical calculations of where that planet, where Mars is going to be located so that our spaceship can get there in this predetermined, pre-calculated path is incredible. And the fact that we can make those calculations based on a theory about a heliocentric model is just absolutely insane. And the fact that someone came up with that like oodles and oodles of years ago, holy bananas! That is just absolutely ridiculous. So it's kind of cool, science and all, and math and things, and just the way that it's all unraveled. But of course, we need to think back and appreciate some of the previous thoughts that we had. Because flat Earth, yeah, it's not true. It's not something that exists. We know Earth isn't flat anymore. But without flat Earth, we never would have questioned flat Earth. And without questioning flat Earth, we never would have gotten to the point where, hey, maybe Earth isn't flat, it's spherical. You have to trust the process. You have to appreciate what you've gone through to get to where you are today. Anywho, that's enough of my rant. Earth is cool. The heliocentric model, even better. Earth's not flat. I hope you learned lots today, and I hope you appreciate all of the theories that we've gone through to get to what we've got today. And that's all for me. Adios, amigos.